I know more people are joining actually, but let me slowly start with the session. So good morning, everyone here in Australia, and good evening, Wei. Welcome to this LCTW talk. My name is Jinge Zhu. I'll be hosting this talk. It's our great pleasure to have Professor Wei Yu from the University of Toronto. As we were saying, it's actually 8 p.m. evening in Toronto, so thanks a lot, Wei, for taking the time giving us the talk. Let me first give a short introduction to Professor Yu. We received his bachelor degree in computer engineering and mathematics from the University of Toronto in Canada in 1997, and master and PhD degrees in electrical engineering from Stanford in 1998 and 2002, respectively. He is now a professor in the electrical and computer engineering department at the University of Toronto, where he holds a Canada Research Chair in Information Theory and Wireless Communications. He is a fellow of IEEE, a fellow of the Canadian Academy of Engineering, and a member of the College of New Scholars, Artists, and Scientists of the Royal Society of Canada. We received numerous paper awards, including IEEE Marconi Prize Paper Award in Wireless Communication in 2019, the IEEE Communication Society Award for Advances in Communication in 2019, the IEEE Signal Processing Society Best Paper Award in 2017 and 2008, and the Journal of Communications and Networks Best Paper Award in 2017. And okay, it's still it's a lot. And the IEEE Communication Society Best Tutorial Paper Award in 2015. He's currently the president of the IEEE Information Theory Society. Actually, I learned about the last one, the president of the Information Theory Society, when I was reading the latest newsletter from Information Society a few weeks ago. I saw Wei's photo on the front page, so that's a great achievement. Congratulations, and of course, thank you very much for the service made to the community. So today we will be talking about intelligent reflecting surfaces. I think that's a very hot topic today. So yeah, without further ado, I'll pass it to you. The floor is yours, Wei.
Okay, thank you. Thank you for the introduction. So let me share my screen. Okay, so it's a great pleasure to be here, well, virtually. I wish I could be in Australia physically. Okay, so the title of this talk is Learning to Beamform and to Reflect Without Explicit Channel Estimation. So this is joint work with my student, Tao Jiang, and postdoc, Hey Victor Chen. We're from the University of Toronto. So this talk is about optimization of communication systems. In communication system design, you often encounter many high-dimensional complex optimization problems. So here's an example. If you look at 5G wireless cellular communication systems, one of the key technologies is a millimeter wave massive MIMO system. So here we have a base station equipped with a large number of antenna array. And one of the optimization problems that you have to perform is to design the beamformers at the base station so that it can target, or it can beamform to the user, to the target user. So a typical base station will serve many users, and you have to design many of these beamformers at the base station. Now, conventional communication system design is always done as a two-step process. So first you have to estimate the channel, and then based on the estimated channel, you perform system optimization. Now, one of the problems with these large-scale deployment is that channel estimation becomes more and more difficult to do, especially when you have a large number of antennas and you have a large number of users. And this is particularly true for massive MIMO system. For example, we have fewer number of RF chains as number of antennas, so that you have to estimate a high-dimensional object, high-dimensional matrix, channel matrix, based on these sort of low-dimensional observations. So channel estimation is a challenging task in these high-dimensional problems. So the main idea of this talk is the following. We ask the following question: is it possible to bypass the channel estimation step and directly optimize the system. So our approach is, yes, we can do this, and we're going to use a machine learning approach to bypass channel estimation and to directly optimize the system, and we're going to show the advantage of this machine learning approach. So this talk will primarily focus on the so-called intelligent reflective surface environments. So this is sort of new devices you can insert into a wireless environment to enhance the transmission between a source and a destination. So an RS is a reflective surface comprised of a large number of intelligent scatters. So the idea is the incoming electromagnetic wave can be re-radiated toward the intended user. And what IRS does is it can adjust the phase shifts of these radiation. So because you have large number of elements in this IRS, then by collectively adjust the phases of all these elements, then you can achieve these passive beamforming gain. And this is especially useful when you have, say, a blocked path from the base station to the users. Then by going through this IRS path, then you can get a better propagation environment. So these IRS are controlled by a controller, and the controller will take into account the channel environment and to adjust these phase shifts appropriately to achieve a system objective. So there are many different applications of these IRS environment. For example, for improving network coverage, for boosting wireless spectral efficiency, for reduce power consumption, to enhance security, etc. So this become very popular topic nowadays. So if you look at the optimization of this IRS system, then if you pursue the conventional approach, then you still have to design this as a two-step process. That is, first you have to estimate the channel. So here there are 3 channels to estimate: the direct channel, as well as the base station to RS and the RS to the user. So you have to estimate all these three different channels. Then based on this estimated channel, then you have to pursue this system optimization. Now, channel estimation for RS is actually a challenging task. This is because RS cannot perform active signal transmission and reception. It's a reflector, so it does not have RF chance. And secondly, the RS system has a large number of passive elements, so there are many channel coefficients to estimate. So to estimate the channel for RS is actually a non-trivial problem. And further, even if the channel is already estimated, okay, so only after, even if you already have estimated channel, the optimization of the system, the overall system, is still a challenging task. This is because we have a large number of phase shifts to optimize. So this means that we're dealing with a high dimensional problem, and typically such problems are non-convex. So even if you know the channel, the solution to this problem is solving the problem is not a trivial task. So in this talk, we're going to tackle these 2 problems at once. So our idea is that we're going to optimize this system objective based on the received pilots, but without going through the explicit channel estimation step. And we can do that. We can pursue this program of bypassing transformation by taking a machine learning approach. So if you think about what mathematical optimization is, or mathematical programming is, mathematical programming is suited for highly structured problems over highly structured models over well-defined problems. And finding a solution relies on specific and often convex optimization landscape. So the traditional design for communication engineering is always based on the philosophy of to model first, then to optimize. So by model, what we mean is we define this optimization landscape, so then we can search through the parameter space to find what the optimal solution is. But what modern machine learning paradigm allows us to do is that if you think of what the optimization problem is really a mapping from the model to the optimized solution. So what we can do is we can design a neural network that takes the model as the input and produce the output, produce a solution as output directly. So here's a pictorial view of what I've been thinking about. So if you think of what a mathematical algorithm is, and the mathematical algorithm is basically something that takes a problem instance as input and produce an optimized solution as output, right? So if you do gradient search, this is what it is, giving an optimization landscape, or produce what optimal solution. So what we can do is we can replace this algorithm by a neural network. So what we can do is to mimic what the algorithm, we can ask a neural network to mimic what the algorithm does. So for example, here we can do a supervised training. We can give many different problem instances to the algorithm and to see what the optimal solution will look like. Then we're going to train a neural network to produce the same input-output mapping. So when a new problem instance comes along, then we can just use neural network and run this neural network to get the optimized solution. Okay. So this is the data-driven approach that I'm going to use to tackle the problem with RS, system level optimization. And this is made possible because the neural network, if you have enough neurons and if you have enough layers, it's a universal function map from the input to the output. So it can mimic any kind of input-output relationship. One of the key advantages of using this neural network approach to solve optimization problem is that we no longer need to parameterize the problem for the purpose of efficient algorithm. In other words, we can define problems through many different kinds of parameter space, and we can solve poorly defined problems, and we can incorporate lots of different type of data as part of the problem definition. And this is all made possible because nowadays we have highly parallelizable implementation structure for both the training and the running of the neural network. So the main idea of this talk is the following. I think of the role of machine learning for communication design as follows. Traditionally, communication engineers have invested heavily on channel models. But these models are inherently only an approximation of the reality. Okay? And further, model parameters need to be estimated, and there's always inherent estimation error. But what the machine learning approach allows us to do is to skip this channel modeling stage altogether and pursue an end-to-end design, end-to-end communication design. So here are some of the advantages of this machine learning approach. It allows us to do direct system optimization without the intermediate step of channel estimation. It allows us to implicitly account for the channel estimation error. We can now easily incorporate additional information, such as location. So for example, if you optimize a millimeter wave system, then the location of the user relative to the base station, it already gives you a lot of information about how the beamformer should be designed. But in a traditional channel estimation based approach, there's no easy way to incorporate this location information. But now with a neural network, you can easily incorporate this location information. And our overall objective is to reduce the amount of pilots needed to arrive at an optimized solution. Of course, neural networks also has lots of neural network approach also has lots of challenges. We need to design the framework to tailor to different system architectures and objectives. So I'll use IRS as an example to see how we should design the neural network specifically for the RS system. Another challenge is generalizability. We want to design a neural network that can be generalized to different system parameters and not just for a particular channel instance. We want to be able to interpret the obtained solution. That's another challenge. And overall, all of this takes quite a bit of training data as well as to make this work. So I'll give some example in this talk. So in this talk, I'm going to give an example of a high dimensional optimization of the communication system. I'm going to use this multi-user beamforming and reflective coefficient design for IRS system as an example. And the same approach can also be applied to the massive MIMO system that I talked about earlier. Okay, so this is the overall philosophy behind this talk. And then now let me go back to the intelligent reflective surface, also known as reconfigurable intelligent surface, RITS. Okay, so as mentioned before, IRS is a reflective surface comprised of large number of intelligent scatters, and the controller will control this phase shift of the scatter in order to provide a better channel for these users. Okay, so the reflected path combined with the directed path need to be optimized by tuning the scatters on the surface. So as I mentioned before, channel estimation is a challenging problem, and system optimization is also a challenging problem, and we're going to use a machine learning approach to solve these two problems at the same time. So let me establish the channel model for the IRS system. So consider a base station with m antennas and IRS with n elements, and let's let k to be number of users. So the overall channel model is defined by this n by m matrix from the base station to the IRS. Then we have the reflected channel HR, there are k of them, one to each of these users. This is h1 to hk. Then there's a direct channel HD, also from 1 to k. Okay, so this is 1 by n, this is 1 by n vector, this is 1 by n vector. So this is the overall channel model. So the idea is that we're going to design the reflected coefficients. So here, these reflective phase shift is denoted as V. So V is e to the j theta at each of these elements. Then we're going to design this V, and as well as design the beamformers at the base station, so that each of the user gets a high signal to noise ratio. Okay, so there's one beamformer for each of these users. So this is a channel model for the IRS system. So if you look at the received signal at the RS, this RK, this is a combination of the direct channel plus the reflected path. So the reflected path goes through this G plus the times the phase shift at the RS, as well as the channel from the RS to the users. So here S is the transmit symbol by the base station, and W is the beamformer for the user J. So this channel has two components, the direct channel and the reflected channel. The reflected channel is a linear function of V, so I can combine this G and H together and call this A. So this A is basically the cascade channel from the user to the RS, and V is how this the phase shift can affect the cascaded channel. So the overall achievable rate for the user is the log of 1 plus the signal to noise ratio, where the signal is the beamformer for user K passing through this channel, then everybody else's beamformer becomes the interference plus and noise. So the objective is to maximize some function of this achievable rate. And we want to do this, the parameter we're going to design are WK and V, the beamformer at the base station, as well as the phase shift at the RS. And these are the functions of the channels. So in the traditional approach, we first estimate the channel, the cascaded channel A, as well as the direct channel. Then we design W and K. In the machine learning approach, I'm trying to bypass this channel estimation stage, and we're going to design this directly. Okay. Now, in either case, we rely on the pilot transmission stage to tell us something about the channel. Then based on the channel, we're going to design the W and V. So let me talk about the pilot transmission stage. So here we assume uplink, downlink reciprocity. So the uplink channel and the downlink channel are reciprocals of each other. So we do a pilot transmission in the uplink stage. So we have user 1 to K each transmit a pilot signal in the uplink. And the received signal at the base station is basically the direct channel plus, again, the cascaded channel through the IRS. And this V is the phase shift at the RS. So this is the received signal at the pilot. Now, if you formulate the overall optimization problem, then you can think of this overall problem formulation as to design the optimized beamformer W and reflected coefficient V based on the received pilots. Okay, so you can think of this overall optimization as finding a mapping from the received pilot to the optimized beamformer, so that some function, some utility function of the rates of R1 to RK is maximized. In the conventional approach, we take this Y, first estimate the channel, then we optimize. But we can potentially bypass this stage and just optimize this functional mapping from Y to W and V directly. And this is the machine learning approach that we're gonna pursue. Okay, so the overall problem is based on the receive pilot, which tell us something about the channel, how do we find W and V? And our objective is to maximize some utility function of the rates, okay, subject to the clock constraint. So this is now our overall problem formulation. So let's first look at how the conventional approach will solve this problem. The conventional approach is based on channel estimation, right? So we first estimate the channel, then we based on the estimate channel, we design the optimized parameter. So how does the channel estimation work? So you see that you need to estimate the cascade channel, both from user to the RS as well from the RS to the base station. So one way to do this is to transmit a pilot, but then we divide this pilot into tall subframes. And what we do is we have orthogonal pilots transmitting at each of these subframes. We repeat those pilots tall times. Then we let the RS to use different random phase shifts in each of these subframes. Okay. So then overall in each subframe, we get this received pilots. So then what we do is we take this received pilots, we do a match filtering with respect to the orthogonal pilots, and this will give us the received pilot in frame T. Then we take tall of these, we have tall subframes, so we stack them together. So this is the overall received signal that we have. So if you look at the relationship between the received pilot and the channel, so we also stack the channel together. Channel is H is a direct channel, A is the cascade channel. Then we arrived at this equation that the received pilot is some function, some linear function of the channel. Then we can pursue an MSE program to find the optimized, to find the channel estimate. Okay, so this is fairly complicated because we have a cascaded channel, but it's something that you can write down. In fact, if you assume that these channels are Gaussian, then you can write down the linear MMSE estimator, and it has a closed form. So this FK has this closed form solution. If you use the square arrow as the criteria for channel estimation. Now, if you look at this channel estimation process, you realize that when you do the channel estimation, you need to define this criteria. You need to define this loss function. And the commonly used loss function is a square loss. And this is because we have a closed form solution when we use this square loss function. But this MSE, this minimum mean square error criteria, does not necessarily correspond to the ultimate system objective of maximizing rate. So this is just for convenience only. So if you insist on this square criteria, you might be overestimating parts of the channel and not estimating enough about some other parts of the channel that you're really interested in. So there's potential then to combine the channel estimation stage and the optimization together, and you can potentially get a better performance. And this is what we're going to do. Okay. All right. So the conventional approach is to do the MMSE estimator for the channel. Then once the channel is estimated, then you have to use some kind of optimization algorithm to do beamforming and the reflected coefficient design. Now this is a non-convex problem, so typically you do some kind of block coordinate descent or some kind of local search to find an optimized solution. You don't necessarily get a global optimum, but you usually get a pretty good solution using these numerical techniques. Okay, so this is the channel estimation-based strategy for designing the IRS system. So what we're going to do is something different. We're going to use a machine learning approach to solve this problem. So we can think about the overall problem as mapping the received pilots to the optimized beamformer at the base station or the reflected coefficient at the IRS. So then what we can do is we can design a neural network that still takes the received pilots as input. So we still do the match filtering with respect to each of these users to get the received pilots for each of these users, Y1 to YK. And we let this to be the input to the neural network. And what we're going to do is we're going to train this neural network so that the produced W, the phase shifts, and so V, the phase shift, and the W, the beamform at the base station, so that the produced V and W is something that optimizes the overall system objective. So what we can do is we can generate many different instances of this channel. For each of these channels, we transmit pilots and then let neural network observe what the received pilot is. Then it will produce V and W. Then we're going to adjust the neural network weights so that the overall system objective is optimized. Okay, so this is like an unsupervised training, but with the loss function. And this loss function is, for example, the sum rate of the overall system, right? Minus the sum rate of the overall system. So then we generate many, many instances of this channel. Then through many of these pilot transmissions, then we can eventually train a neural network that's able to directly map the received pilots to the optimized system parameters. And this is the main idea that we pursue. Okay, so we're going to use this proposed deep learning framework to adjust the neural network weights to maximize the system utility. Now, what kind of neural network should you use? Well, you can use a fully connected neural network, and it does work. But we also want to sort of explore the system sort of geometry here. So you see this neural network produce two types of output. One is the reflected coefficients, IRS. The other is a beamformer, W. But these beamformers are for the users, and this V is for the RS. And this RS and user are sort of have a relative, this RS serves these users, so there's relative relationship between these RS and users. So this brought us to the question of what kind of neural network architecture is the best to capture this relationship between the RS and the users. And specifically, the kind of relationship we want to capture is that the output of the neural network should be so-called permutation invariant and permutation equivariant with respect to the users. What I mean is as follows. If you look at this neural network, if they have users 1 to k, if I relabel these users, so suppose I do a permutation of these users, then what should happen is that this V design at RS should be the same, right? The RS reflected coefficient should be invariant to the relabeling of these user indices. So this is called permutation invariant, okay? On the other hand, this W should be permutation equivariant in the sense that if I relabel users 1 and 2, then this W1 should become W2 and W2 should become W1, okay? So if you use a fully connected neural network, it does not have this permutation invariant and permutation equivariant property with respect to V and W. So what we should do is design a neural network that enforces this kind of permutation invariant and permutation equivariance. And the kind of neural network that does this is so-called graph neural network, and this graph neural network captures the relationship between the RS and users. Okay, so here's the graph neural network we have designed. So the neural network takes y1 to yk as input and produce W. This is the beamformer coefficients at the base station, and the V, which is the reflected coefficients at the RS. So this neural network has D layers, okay? And this is the plus the input layer and the output layer. The output layer is just a normalization layer. And the input layer is a small DNN, one for each of these users. So there's k branches of this DNN, one for each user, and there's another branch corresponding to the RS. The RS branch does not have inputs because the pilots is with respect to the users. So what the RS branch does is takes the output of this first layer as the input to the first DNN for the RS branch. Okay? Now we're going to design these aggregation and combination units in each layer as well as this DNNs in such a way that the overall DNN architecture is permutation equivariant with respect to each of this user. In other words, if y1 and y2 permutes, then this w1, w2 should also permute, okay? And it's permutation invariant with respect to RS. That means if y1, y2 permute, then the V will stay the same, okay? So then we're gonna design this aggregation and combination units such that this is true. Now, first of all, you see that the input to this IRS DNN is the mean function of the output of all these DNNs. So this mean function is permutation invariant because the mean of the k variables, doesn't matter how you commute it, the mean is still the same. And this aggregation combination units are also designed in such a way that they are permutation equivariant and permutation invariant. Okay, so let me zoom into each of these boxes and to tell you where they are. So here is at the RS side, this is the combination aggregation unit at the RS side. So what it is that it has a DNN, a sub-DNN, correspond to Z0. Z0 is the RS node. Then it takes the input from these k users, Z1 to Zk. But it uses the mean function to summarize the input from all these k users. And this mean function is permutation invariant. So then the overall system becomes, this overall block becomes permutation invariant with respect to Z1 and Zk. If you permute them, the output stayed the same. Okay, so this is how we made the RS unit permutation invariant. Okay, so this is the IRS unit, this unit here, and all of these are these combination and aggregation units. And the second, this is the combination and aggregation unit for the users. So again, Z0 correspond to the DNN to the RS. Then Zk, this is for kth user. So what it does, it take all the other users, Z1 to Zk minus 1, then Zk plus 1 to Zk, take all of them, then it uses a max function on the output of this DNN. And this max function is also permutation invariant, right? So if you permute these, the max doesn't change, then this max plus its own Zk plus the Z0 corresponding to RS becomes the input to the DNN. Okay, so these are the inputs, then we get Zk. So Zk is the output of this one unit. Okay, so Zk is output this unit. Then this Zk goes to another layer, you get Z1 in layer 2, Z1 from layer 2 up to Z1 to layer D. Then finally you do a linear layer, then the normalization layer is just to enforce the power constraint. Okay, so this aggregation and combination units are all designed in such a way that it respect the permutation invariant and equivariant properties of this IR system. Okay, so this is the overall DNN architecture that we designed. So further, to reduce complexity, the DNN parameters are tied across the users. So all of the users have the same DNN parameter. So when you do the backpropagation to train, then they're triggering one set of parameters is being trained. And so this makes the DNN generalizable to scenario with many different users. So what we can do is we can train a neural network with k users. When we have another user come in, we can just add another branch to the DNN. We don't have to retrain the DNN. So that make it generalizable with respect to number of users. Okay, so this is the how we're going to do this. We're going to design the DNN. Okay, so let me tell you now how well this works. So here's a simulation setting of a base station located at this location. They have RS at the YZ plane, and we have K users located in this box. So we assume that there are 8 antennas at the base station and 100, this is a 10 by 10 RS system. And we have 3 users here, and we assume that the direct path is a radially fading channel, so it does not have a line of sight. But the base station to the RS system has a line of sight, and the RS to the user system also has a line of sight. Okay, so this is the Rician model for the base station to IRS and IRS to the users. So the DNN parameters are as follows. the parameters are basically the parameters of each of these F0, F1, F2, F3, F4 functions. So these are these functions. F1 is here, F3 is here, F4 is here, so F2 is here, and F0 are these functions. So we're going to train the parameters of these functions. This is the size of this DNN. Okay. We iterate 100 times to update the GNN parameters, and each iteration we use 1024 training samples to compute the gradient. So benchmarks are the perfect CSI case with the block coordinate descent. So this is one benchmark. And the other is the linear MMSE channel estimation with block coordinate descent. This is to do the channel estimation first, then to then to design a system. And to be fair, we also compare with the case where we use a deep learning method to do the channel estimation. But then once the channel is estimated, then we do the system level optimization using block coordinate descent. So this, by comparing with these three benchmarks, we can truly see the benefit of this joint design, benefit of this combined design. So here's an example of a simulation of maximized sum rate as a function of pilot length, the overall pilot length at these parameters. This is the transmit power in the uplink pilot stage and the downlink downlink estimation stage. So the yellow curve is the perfect CSI case. We get about 5.5 bits per second per hertz. The purple and the red curve are the DNN designs, the deep learning approach. So as I mentioned before, one of the advantages of the DNN approach is that it can incorporate different kinds of information. So here is an example. If you incorporate location information, this is the purple curve. And if you do not incorporate location information, only use the receive pilots, then this is the red curve. So this is how the sum rate improves as a function of the pilot length. And this is to be compared with the traditional MMSE channel estimation first approach. So this is the red curve using linear MMSE channel estimation. You see that to achieve the same rate, you need a lot more pilots. So the main advantage of this DNN approach is that it will save the amount of pilots needed to achieve a certain performance target. And this can be significant. This black curve is a case where you use a deep learning module to estimate a channel. Then once the channels are estimated, you do the block coordinate descent. You see that it already does better than the linear MMSE approach, but it does not do as well as if you combine the channel estimation and the optimization together. So this is really the advantage of bypassing the channel estimation. Okay, so this is the plot of downlink sum rate versus the uplink pilots. So here's to show you how fast these channel estimation approach converge over training epochs. You see that with different pilots, they all converge pretty fast. So each epoch requires this many channel samples. So this is not a trivial amount of training sample, but the convergence rate is pretty good. So one of the things we want to test is the generalizability performance of this result. So here is the generalizability of the proposed approach with respect to transmit power. So the yellow curve is again a perfect CSI plus block coordinate descent curve. So the red curve is if you use a deep learning approach, then train at each of these power levels. So the purple curve is if you train at 15 dBm input transmit power, and you test the system at a different powers. So you see that at 15 dBm, you get the purple curve is the same as the red. And the green curve is if you train at a 25 dBm, then test it at very different power. You see that if the testing power and the training power are different, then you get performance degradation. But the performance degradation is not a lot. If you over this 10 dB range of the transmit power, all of these curves still outperform the MMSE based approach. So this is generalizability with respect to the downlink transmit power. And generalizability with the uplink pilot transmit power is similar. Here we see that the performance is not very sensitive with respect to the uplink transmit power. So generalizability is important, and generalizability with respect to number of users is also important. So here's a plot of the sum rate with respect to number of users. And again, you see that deep learning approach outperforms the MMSE approach for any number of users. So this is trained for k equal to 6. We're trained for 6 users. We just add another branch to get 7 users, 8 users. We delete the branch to get 5 users, 4 users. You see that in all of these that we are outperforming the MMSE approach. We can also train the neural network for maximizing the minimum rate. So here I'm plotting the empirical CDF curve as a function of minimum rate for many different channel realizations. You see that this deep learning approach, which is the red curve, is doing better than the LMNSE approach. And this is for the case of pilots equal 75. So it doesn't quite get to the perfect CSI case, but it's getting close. So here's the generalizability with respect to number of users. I'm gonna skip that for the minimum rate. So it's the same kind of idea. If you train this at a particular number of users, here I'm training for 3 users, then use it for 2 users or 4 users, you see that this deep learning approach always outperform the LMMSE approach. Depends on the amount of pilots. There's always a gap with respect to the perfect CSI. Okay, so these are the generalizability results. Now, one of the things that we really want to understand is what is this DNN doing? We want to interpret the solutions from this DNN. So this is important for us. So in the last part of this talk, I'm going to visualize the solution we obtained from the graph neural network and to make a case that's actually doing the right thing. Okay. So here what we do is we're going to train the proposed GNN, proposed graph neural network for a single user case. Then we're going to use the array response to interpret the resulting beamforming pattern from a GNN. Okay. So what I mean is follows. If you think of the array response at the M antenna base station, it's the array response of the base station times the beamformer that we designed. So we can see that which direction the elevation angle and azimuth angle is this beamformer targeting. Okay, so this is the array response of the base station. And there's also the array response of the IRS. So if you have an L by L IRS system, you can write the array response of the IRS as a function of the azimuth and elevation angle of the incoming wave, as well as the azimuth and elevation angle of the outgoing wave. Okay, so this is the array response times the diagonal times the phase shift times the array response of the incoming wave. Okay, so that depends on, that's a function of how you set the phase shifts. Okay, and by the geometry, based on how the IRS is tilted, and if you have IRS on the YZ plane, then this is the IRS array response that you would get from electromagnetics. So here's the simulation setting. Here the base station here have RS, here have the user here, and each they have the azimuth and elevation angles. And the angle, the geometry of this angle is given here. It's given by phi 1 theta 1 star, phi 1 star theta 1 star, phi 2 star theta 1 2 star, and phi 3 theta 3. Because these are the angles that we use to do this testing. All right, so this is where we get. So this is the IRS array response after the neural network is trained. You see that it's the ideal, the actual angle is at 0.5 and minus 0.5, and indeed this IRS is adjusting its phase shifts in such a way that it gets a targeted response exactly at this minus 0.5 at plus 0.5 range. And if we move the user to a different location, then you see that this target will switch to a different location. And this is the learned IRS array response by training a DNA. What about at the base station? So this is the array response at the base station. Base station is a function of theta 1. You see that the base station to the RS is always maximized at the actual angle. This here in this case is 2.3. And even if the users move to a different location, this base station array response still stay the same. So it still stay. So our base station is still targeting toward the RS, and that then what it's doing is let RS to reflect to a different angle. So you see that this is the case when you have a 10 by 10 RS and a antenna base station is really doing the right thing. Okay, so it gives us a lot of confidence that the machine learning is actually working as intended. So here's some plots with different sizes. This RS, this is 3 by 10, this is 5 by 10, this is 10 by 10. You see that if you have a smaller RS, then your focusing ability gets worse. If you have a larger RS, then you will be able to focus on exactly the right location. So you see that the size of the RS does matter. And in the final plot, I'll show you a case when you have 3 users. So here you have a base station, then you have IRS, here you have 3 different users located at 3 different places. So again, this is the RS array response as a function of the azimuth and the elevation angles. You see that it is doing the right thing because it's focusing on 3 different locations here, here, and here, correspond to the angles of user 1, user 2, and user 3. And what about the base station? The base station designs 3 different beamforming vectors, and these beamformers are peaking at this location, and this location, and this location, okay? But what's interesting is that this focusing ability for these 3 different users are different, right? So it's much better in focusing for this user, but it's not as well for focusing this user, and it's worse for focusing this user. And this is actually user 1, this is user 2, and user 3. So what's happening is that if you examine the base station array response for the beamformer, you see that user 1's array response is actually the highest. So what is it doing is the neural network is jointly designing the beamformer at the base station and the reflecting coefficients at RS such that the combined effect of the base station beamformer and the reflected coefficient is such that it is able to reach the user. So it's compensating the weaker focusing for the user 1 at the RS by the stronger array response at the base station, a stronger beamforming at the base station. Okay? So here, what we're doing is we are maximizing the minimum rate for all the 3 users. We're going to make sure that all the 3 users gets a good SNR. And with this kind of objective, the neural network actually takes into account of this objective. We will design the beamformers and the RS reflected patterns in such a way that all of them gets the respective rate. Now, where they peak are slightly different. This is to make sure that they do not interfere with each other. Okay, so you see that in the multi-user beamforming case, the RS and base station are really doing the right thing. Okay, so let me summarize this talk. So in this talk, we show that it is possible to bypass explicit channel estimation for optimizing the beamformer and reflected coefficients in an RS-assisted communication system. And this is accomplished by a graph neural network that maps the received pilots directly to the desired RS configuration and the beamforming matrix at the base station. So we're bypassing this channel estimation stage. And this GNN, the graph neural network, is permutation invariant and equivariant with respect to users. And we show that base station, we can account for user locations. We can incorporate user locations to further enhance the performance. And we see that the GNN can learn to solve both the sum rate and mean rate maximization problems. And what's really interesting to me is to see that the resulting base station beamformer and the coefficients are interpretable. It's doing the right type of focusing just as we expect. And the overall advantage is that this proposed approach is more efficient in terms of the required pattern length. So to conclude, the traditional paradigm for communication system design is to model, then to optimize. And what machine learning allows us to do is to do a data-driven approach that performs multi-user beamforming and reflected coefficient designed without explicit channel estimation. It's implicitly learning the channel and to do optimization. And the same approach can also be used for a massive MIMO system to do channel estimation, feedback, and pre-coding. And the key advantages of this approach is that we are implicitly accounting for model uncertainty and channel estimation error. And the key issues are generalizability, interpretability, and the neural network architecture that match the problem structure. That's very important. I'm really interested in the question of how far can we push machine learning. There are many open questions, and I think still to be solved. So thank you very much for attending this talk. So here are some of the papers. The talk is mostly based on the first paper here, learning to reflect and beamform for intelligent reflected surface with implicit channel estimation. The massive MIMO work is in these two papers, but I didn't have a chance to talk about in this talk, but they use a very similar approach. Okay, so thank you very much.
Thank you, Wei. Very interesting talk. I'm sure there are any questions from the audience. So yeah, actually you can just unmute yourself and speak if you have any question to Wei. I see Jing Hong unmuted himself. Do you have a question?
Yeah, I think I have a couple of questions. Thank you, Jingge. Thank you, Wei. Very interesting talk. And it's good to see the use machine learning can outperform the conventional estimation and optimization approach. I think in your figure, page 18, you show, if you could go to there, please. Oh, maybe not 18, sorry, maybe next, yeah, this one, thank you. And you see even at a very long pilot length, 120, you still have a gap. I mean, for the conventional approach compared to the machine learning approach. I'm wondering, is this due to the conventional approach? I mean, I just try to figure out where the performance gain comes from. Is it due to the channel estimation error, or is it due to the, talking about the conventional channel estimation error, is it due to the optimization problem there? Or we could not optimize it to the best what it could do with machine learning. Is that clear? Sorry.
Yeah. I cannot separate the two because I'm doing a combined approach.
Okay.
So I don't know, right? So I think this will eventually get to the perfect CSI case.
Yeah.
When you get to, because the perfect CSI case is also using a block coordinate descent to do the optimization. So they're all doing the optimization part is the same. So it's really just due to the not knowing the channel well enough. Because there are many channel parameters to estimate. There's 100 n equal to 8. There's 800 parameters just from the base station to the RS, and the 300 parameters from the RS to the users. There's 24 parameters from the user to the base station. So this is it's a pretty challenging channel estimation task to perform.
So is it fair to say there is no model uncertainty issue here? Because either you use the conventional approach or your machine learning approach, you are using the same channel model.
Yes.
And
we're using the channel model. So the model is actually correct. I mean, this is an idealized model we use to train the neural network. So both the neural network and the conventional approach assumes the same model. But in reality, if you do have lots of channel measurements that you could use to train the neural network, then you can potentially get a better network. But we're not obtaining that gain. So right now we use the same model in the two approaches. So it's not about model uncertainty. It's just about the ability for the conventional MNSC technique to estimate the channel. I think it's number of parameters that's the problem.
Okay, thank you. So, I think in your last slide, I think, oh, sorry, 31, slide 31, you show this interesting, you show this base station, the figure on the bottom of the left. You show this base station blue and green. Looks like they have this, it's interesting, they have this quite strong side lobes there. And this is interesting. I mean, if you try to compensate, if you try to jointly form beam to the user from the base station and the RS, you probably need to focus on your energy to the user, use a strong May beam. But here the side beam is 1 compared to the May beam 1.4. It's still very strong. Is it because if your RS may have a beam is not accurately pointed to the user, so you need to have this strong side beam to compensate or to cancel that one?
Yeah, exactly. So I did not plot the cascade channel. So what I've really done is to do the user, right? This is the beamformer at the base station, combine with what the RS does, then to see what's the combined beam will look like for the user.
Okay, yeah.
So this is just for user one signal, what the base station is doing. But when this signal hit the RS does this, right?
Yeah.
Then by the time it gets to the user, it's hard to tell what exactly is happening.
Okay, yeah.
So this green thing, again, is through this, then the red is through this. So what we can say is that the RS is roughly focusing on the location of the user, as shown here. And the beamformer are roughly toward the location of RS, but there are variations of it. And the variations is expected because you don't want the users to be on top of each other, otherwise they'll be interfering. But then what you want to do is, where you want this signal after being reflected so that they become resolvable. It becomes kind of a zero forcing solution.
Okay.
But it's hard to see exactly. And there's also a direct path. We have a radiating direct path too. So it may be that with the direct path, then certain parts will be constructively interfered, certain parts will be destructively interfered, so that they become more resolvable than it shows here.
Okay, thank you very much, Wei.
Thanks for the questions. Any other questions?
Can I ask a question here? Can you hear me?
Yes.
Yeah, okay. What's the wavelength here? Or the frequency or whatever. The wavelength determines the size of the array, right?
Yeah, it's a function of size array. So lambda over, like I don't remember exactly where we did this simulation on, but it's the spacing. I mean, if you keep the spacing divided by lambda c as lambda as spacing as lambda over 2, then it's sort of normalized.
Yeah, but I mean, if your lambda is big, then the array is big, and then you can focus on different parts of the array from the base station, rather than just you won't have, rather you can resolve maybe different parts of the surface, the reflecting surface, if that surface is big, right?
It's correct. It's correct. Yeah, maybe it could be that it's actually doing that. It's not clear. Yeah,
but I mean, I think all these distances should be normalized to the wavelength.
That's right. That's right. Absolutely. But this is 100 meters, so it's very far compared to the wavelength. So say 3 gig, we're talking about a few centimeters wavelength.
These are meters, are they? Okay.
Yeah, these are 100 meters. This is a distance.
So I mean, if we know the wavelength, and we know the size of that reflective surface, and whether, okay.
Right. But it's a far field. I mean, we're not talking about near field.
All right, okay. Another question is, what happens if you just switch off the direct path?
You can do the same thing. We just happen to include the direct path. If you don't have direct path of a block, then you can do the training accordingly.
But did you have a certain ratio of powers or not going on the direct path? You didn't, no.
We have a Rayleigh fading channel. So
yeah,
in the direct path, we have a rising channel with a direct line of sight in the direct path.
Yeah, okay.
This is the model that we use to train.
All right, but what power on that Rayleigh fading channel?
Depends on the distance.
Okay, so it's the same, it's the path loss.
That's right, the path loss is the same. It's the same path loss exponent applied to this path versus this path and this path.
Yeah.
But these two paths have a line of sight and this path does not.
Okay, all right, thank you very much.
Thanks. Other questions?
Hi, Wei. I have a question regarding the use of machine learning, right? So nice work. We start everything from an optimization problem, right? But in the end, are we able to achieve the globally optimum solution?
No, we cannot.
But do we know how far are we from, the upper bound?
So for this problem, we are this far.
That one is not upper bound, right? Wait, come on, you're using BCD.
Yeah, that's right. This is block coordinate descent. So you could do better than that. We're not even get to the block coordinate descent.
Yeah, the problem is that why can't we just using machine learning to somehow, get more compared to the upper bound in here?
It's potentially possible.
Okay. So have you tried to increase the pilot length to 1,000 or whatever?
No, we have already saturated.
Okay,
right? So we're not getting upper bound. This is because we don't have a precise channel, right? We are still.
No, what if I give you the precise channel? What if I give you the precise channel? So what information is missing in the machine learning core to bridge the gap? Yeah, that's something I want to ask.
You need to somehow explore every sort of valley and hill on the optimization landscape.
Right.
It's not like the training. The main point of this work is so that you don't have to first to model the channel. We're not really using the machine learning to efficiently, it's not like a quantum annealing or something like that, to efficiently search every possible local optimum.
I understand, So, but from your point of view, is it possible to use machine learning to get the globally optimum one? I suppose I use branch and bound or whatever, and then it's possible to use my machine learning core to mimic what happened in that globally optimum algorithm?
Whatever globally algorithm needs,
non-polynomial time one?
Yeah, whatever globally optimal solution algorithm you design needs to explore all these local optimums.
Right.
There's no way to bypass that.
If you don't have a nice structure in your problem, right? If the problem has some property, then it may give you some hints to locate the globally optimum. You don't have to go over all the,
Yeah, so this is a different parameterization. Okay, so in this talk, we're doing it. So we have a different parameterization of the problem.
Right.
So we no longer parameterize the problem as a function of the channel coefficient of this 8x100 channel.
Mm-hmm.
Rather, we just use receive pilot as the parameterization of the problem. Okay, that's what we're doing. So, but reparameterization, this reparameterization does not shape the optimization landscape in such a way that it becomes easier to find the global optimum.
Right.
So you want to find a way, something that allows you to find the global optimum. You need to find sort of how to reparameterize the problem so that the search becomes more efficient. Okay. And I don't think we're at a stage that we can use machine learning to do that yet.
Okay, thank you, Wei. Thank you very much.
Sense?
Yep. Thank you. Yep.
Yeah, thank you for the question.
Thanks. Yeah, if I could ask a quick question here. So one point I particularly like about this work is you kind of design your network architecture by exploiting the structure of the problem. Right? I'm just wondering, have you compared to the performance when you just use a, for example, a complete DNN, and what's the gain of this, judiciously chosen structure of your network?
Yeah, we did. So actually, in the first conference version of the paper, we just use a fully connected DNN. So then we started to use this graph neural network, and we get much better performance. And the main motivation for us is actually generalizability. We don't want to say retrain a DNN. We have 5 users, then if you have 6 users, you have to retrain again, and that's labor intensive. So we want to use a DNN architecture that naturally generalized to more number of users, and that's our main motivation. And performance-wise, also there's performance gain because it's just a better match between the DNN architecture and the problem structure.
I see. Thanks. So actually, also commenting on Derek's comment. So is there an attempt actually to generalize this, say, for some generic mathematical optimization problem, you can design a specific structure of the DNN which matches to the structure of the problem, and maybe say something more about even the optimality or suboptimality of the solution of the problem.
You could, right? So suppose you could design a DNN to solve linear programming. So if you have input as a parameter of linear programming problem, and somehow magically the output, after seeing enough of linear programming, they figure out this is this is what the input-output relationship. So theoretically, it's possible, but it's difficult to generalize, right? If you have linear programming is a particular matrix size, if you change the matrix size, now you have to retrain the neural network. My feeling is that if you have a problem as nice as linear programming or STP or something like that, then you should use a conventional optimization because it's been tailored to that problem structure. Only when the problems are ill-defined, only if that we don't have a good parameterization of the problem, or maybe the parameterization is too complex. For example, in this case, RS, we have 100 elements. We have 100 by 8 channel elements. When the complex, the parameterization doesn't seem to be natural anymore, then that's when you try to see whether you can use machine learning to have a better parameterization. So that's my view. I don't think you should use machine learning to solve problems that already have invested so much time, like I don't know, decoding or channel coding or something. Because if you know the channel model exactly, then you should use what we already know.
Yeah, I agree. Thanks for the insight. So I think we can take the last question if there's any. All right. Okay. So yeah. Then there's a comment from Peng. Do you want to say something about that?
So the question is, I think it depends on the different problem structure. For some special problem, you use machine learning to derive global optimal solutions. I don't know this. I would love to learn about literature on this.
Yeah. Do you wish to say something about MIN Ming LP Peng, or that's your everything? All right. Okay. So yeah, I think if there's no more comments, yeah, thank everyone for joining us. Just a quick announcement: we will have a break for this LCTW series, along with the semester break here, and we will resume in August, I think. And we still have a few open slots towards the end of this year. So if there's anyone who wants to give a talk, feel free to reach out to either Wancheng or myself. Okay, so yeah, thanks again, Wei, for this very interesting talk, and thanks everyone for coming.
Thank you, Wei. Thank you.
Thank you.
Thanks. Okay, bye everyone.
Bye-bye. Take care.
Bye.
Okay, bye-bye.